Hello everyone, welcome back to the channel. Today we're diving into a fundamental design pattern in software development, the singleton pattern. In Python, the singleton pattern is a powerful tool when you want to ensure that only one instance of a class is ever created throughout your application. We'll break it down step by step, explain why it's useful, and look at a practical example. Whether you're preparing for a coding interview or just want to sharpen your Python skills, this is a pattern you definitely want in your toolkit. So let's get started. 1. Introduction. The singleton pattern is a well-known creational design pattern that guarantees a class will have only one instance throughout the entire application. This means that no matter how many times you try to create an object from the class, you'll always get the same instance back. It's often used in situations where having multiple instances of a class could cause issues, like managing a shared resource, database connection, or logging mechanism. This pattern makes sure that the instantiation of a class is tightly controlled and always results in the same object. Key characteristics. Now, let's talk about the key characteristics of the singleton pattern. First, it ensures that only a single instance of a class is created, preventing any duplicates. This is crucial when you need to maintain a single, consistent state across your application. Second, the singleton pattern provides a global access point to this instance, allowing any part of your code to interact with it. This makes it convenient to manage shared resources as the same instance is accessible throughout the entire application. 2. What is the singleton pattern? The singleton pattern is essentially about controlling how objects are created to make sure that only one instance of a class exists throughout an entire application. It's like a gatekeeper for object creation. No matter how many times you try to create an object of that class, you'll always get the same one. A great real world analogy is a company's CEO. No matter how many people attempt to appoint a new CEO, the company can only have one, and any reference to the CEO will point to that same person. In software, the singleton pattern works the same way. It ensures that only one instance of a class is created and used globally across the entire application. 3. Why use the singleton pattern? The singleton pattern is especially helpful in situations where having multiple instances of a class could cause problems like resource conflicts, inefficiencies, or inconsistent data. Think about it: if you're managing something like a configuration file, a database connection, or a logging system, having more than one instance could lead to errors or wasted resources. By ensuring that only one instance of the class is ever created, the singleton pattern helps maintain consistency, avoids conflicts, and ensures efficient resource management across the entire application. 4. How to implement the singleton pattern in Python. The singleton pattern in Python can be implemented by overriding the underscore underscore new underscore underscore method, which is responsible for creating new instances of a class. By controlling this method, we can ensure that only one instance of the class is created. This is a simple yet effective way to enforce the singleton design, making sure that whenever we try to create an instance of the class, it always returns the same single instance. Let's dive into how to implement it step by step. Step by step implementation. The singleton pattern can be implemented in Python by overriding the underscore underscore new method. In this approach, the class has a class level attribute underscore instance which is initialized as none. This attribute will hold the single instance of the class. When the underscore underscore new method is called to create a new instance, it first checks if an instance already exists by evaluating if underscore instance is none. If no instance exists, it creates one by calling the super.underscore underscore new method. If an instance already exists, it simply returns that instance. This ensures that every time the class is instantiated, the same object is returned. This approach guarantees that only one instance of the class is created throughout the entire application, effectively implementing the singleton pattern. Simple example. In this example, we implement the singleton design pattern, which ensures that a class can have only one instance throughout the lifetime of one application. As discussed in the earlier response, singleton restricts instantiation by providing a mechanism where subsequent attempts to create an instance return the same single object that was first created. This is useful in scenarios where having multiple instances of a class would lead to unwanted behavior, such as managing shared resources like database connections or configuration settings. The key part of this implementation is the use of the underscore underscore new method, which controls the instantiation process. Normally, underscore underscore new is responsible for creating a new instance of a class, but in the singleton pattern, it checks if an instance already exists by referencing a class attribute underscore instance. If no instance exists, i.e. underscore instance is none, it creates the instance using super singleton class dot underscore underscore new class and stores it in underscore instance. On subsequent calls to create an instance, instead of creating a new object, the method returns the existing instance stored in underscore instance. When we test the pattern by creating two variables singleton1 and singleton2, both variables refer to the same object. This is confirmed by the expression singleton1 is singleton2, which evaluates to true, meaning they are the same instance. This behavior is central to the singleton pattern. Even though we attempt to be through multiple instances of the class, we always end up with a single SWIAD instance. This pattern is especially useful when we need to enforce a single point of access to certain resources, ensuring consistent behavior across different parts of an application. By using this approach, the singleton pattern effectively manages shared resources, preventing the creation of multiple instances that could lead to conflicts or inconsistencies. It simplifies the management of objects that need to be globally accessible and ensures that only one instance of the class is ever created. 5. Real-world use case singleton pattern in action. 1. Logging system. In the context of a logging system, the singleton pattern plays a crucial role in ensuring that only one instance of the logger is created and used throughout the entire application. This single logger instance is responsible for recording events, errors, and operational data, which are essential for tracking the application's behavior and diagnosing issues. By using the singleton pattern, you can guarantee that all log messages, regardless of where they originate in the code, are routed through the same logger instance to a single destination, such as a file, console, or external monitoring service. This ensures a coherent, organized log trail that provides consistent insights into the application state and performance. Without a singleton logger, multiple instances could lead to scattered logs and incomplete data, making it harder to maintain a reliable log history. Why singleton? A singleton logger is essential for maintaining consistency and efficiency in logging throughout an application. Without the singleton pattern, multiple instances of loggers could lead to fragmented logs, where different parts of the application write logs to different locations or at varying times, creating disorganized and incomplete log records. With a single logger instance, all logs are written to a unified location, ensuring consistent logging behavior, which simplifies debugging and monitoring. Additionally, the singleton pattern minimizes resource overhead by preventing the creation of multiple logger objects. This is particularly important in high-volume logging environments where repeated instantiation of logger objects could slow down performance and consume on-top. By ensuring a single globally accessible logger, the singleton pattern optimizes both resource usage and log management. Expanded use case. In a microservice architecture where multiple services are working together, having each service use its own logger could lead to scattered logs across different files or systems. This would make it difficult to track errors, understand the flow of data, or correlate events between services. For example, diagnosing an issue might require piecing together logs from multiple sources, resulting in inefficiencies and higher chance of missing crucial information. By using a singleton logger, all services can log to a centralized location, ensuring consistency. This unified logging makes it much easier to trace errors, monitor performance, and correlate activities across services. A single logger instance across all microservices simplifies the log management process, providing a coherent and complete view of the application's behavior, and makes debugging and performance analysis much more efficient. Practical implementation. In this example, we implement the singleton design pattern for a logging system, ensuring that only one instance of the logger exists across the entire application. As mentioned in the earlier response, the singleton pattern is ideal for situations where a single shared resource is required, such as a logger. This approach ensures that no matter how many times the singleton logger class is instantiated, all references point to the same logger instance. preventing the creation of multiple loggers that could result in duplicated or inconsistent log output. The underscore underscore new method is overridden to control the instantiation process. When an instance of the singleton logger class is requested, the method checks if an instance already exists by reaccess by referencing the class attribute underscore instance. If no instance exists, a new one is created and the logger is initialized via the underscore initialize underscore logger method. If an instance already exists, it simply returns the existing one. This ensures that the logger is initialized only once, even if multiple parts of the application attempt to create new instances of the singleton logger class. The underscore initialize underscore logger method sets up the logger with a unique name, configures it to log at the debug level, and attaches a stream handler to direct log messages to the console. A formatter is also used to define the structure of the log messages, including the timestamp, logger name, log level, and message content. The check if not self.logger.hash handlers ensures that multiple handlers are not added, avoiding the duplication of log messages. In the testing phase, we create two logger instances, logger 1 and logger 2. Since the singleton pattern ensures that only one instance exists, both logger 1 and logger 2 reference the same logger object, as confirmed by the output of print logger 1 is logger 2 returning true. When logging messages using either instance, both messages are routed through the same logger. Messages are routed through the same logger for demonstrating that the singleton pattern is functioning as intended. By using the singleton pattern in this context, we guarantee that the logging system remains consistent and efficient across the entire application. This prevents the creation of multiple loggers that could lead to duplicate logs or scattered output. Instead, the application uses a single shared logger, ensuring centralized control and consistent logging behavior. 2. Database connection. In applications that frequently interact with databases, managing database connections efficiently is crucial. Each time a connection to the database is opened and closed, it consumes valuable resources. If an application creates multiple database connections simultaneously, it can lead to performance bottlenecks, exceeding connection pool limits, or even database crashes. This is especially true in environments with high traffic or heavy database interactions. Using the singleton pattern for database connections helps ensure that the application uses only one connection throughout its lifecycle. This approach prevents the overhead of repeatedly opening and closing connections, thereby optimizing resource usage. Additionally, a singleton connection guarantees consistency in transaction handling, ensuring that all parts of the application interact with the database in a synchronized and predictable manner. This results in better performance, fewer connection-related errors, and more efficient resource management. Why singleton? A singleton for database connections provides several key benefits. By ensuring that only one connection is open at any given time, it helps prevent resource exhaustion, especially in systems that handle high volumes of traffic. This centralized control over the database connection ensures that all parts of the application have access to the same session, promoting consistency and reducing the risk of conflicts. Moreover, a singleton makes managing transactions smoother by preventing issues caused by multiple active connections, such as inconsistent data or failed query. By minimizing the need for repeatedly opening and closing connections, it reduces connection-related bugs and enhances the overall efficiency of database interactions. Expanded use case. In a web application with thousands of users, managing database connections efficiently is crucial. If every user request opened a new database connection, the server could quickly run out of available connections, leading to performance issues or even crashes. By using a singleton pattern for the database connection, the application ensures that all interactions share a single connection or a limited pool of connections, preventing the server from being overwhelmed. This shared connection approach reduces resource usage and helps maintain the application's responsiveness. The singleton pattern also simplifies managing connections by centralizing control, making it easier to handle transactions, maintain consistency, and avoid connection-related bottlenecks. Practical implementation. In this example, we implement a singleton pattern for managing database connections, ensuring that only one instance of the connection is established and shared throughout the application. As explained in the earlier response, the singleton design pattern prevents the creation of multiple instances of a class, making it particularly useful for managing resources such as database connections. This ensures that all parts of the application use the same connection, preventing inefficiencies and potential conflicts that could arise from having multiple connections open simultaneously. The underscore underscore new method is the key to enforcing the singleton behavior. It checks if an instance of single database already exists. If not, it creates a new instance and initializes the connection using the underscore initialize underscore connection method, simulating the process of connecting to a database. If an instance already exists, it returns the existing instance, ensuring that any further attempts to create a new connection return the same object. The class also provides methods such as get underscore connection to retrieve the current database connection and close underscore connection to simulate closing the connection. The singleton pattern ensures that regardless of how many times we reference the class, whether through db1, db2, or any other variable, all references point to the same instance and connection. This is confirmed when b1 is b2 to returns true, indicating that both variables refer to the same object. By using this approach, we ensure that the database connection is consistent across the application. The singleton pattern is particularly useful in situations where opening multiple database connections could lead to inefficiencies or errors. It guarantees that only one connection is maintained, which can be shared and accessed by different parts of the application. Additionally, when the connection is closed through one reference edb1.close underscore connection, the change is reflected across all other references, demonstrating the shared nature of the connection. This makes the singleton pattern an ideal choice for managing shared resources like database connections, ensuring efficient and centralized resource management. 3. Configuration Manager. In many applications, a configuration manager plays a critical role in maintaining key settings like database credentials, API keys, and environment-specific configurations such as development, staging, or production. If multiple instances of a configuration manager are created, there is a risk of inconsistent configurations being read or applied across different parts of the application. This could lead to errors, misconfigurations, or security issues. By using the singleton pattern, the application ensures that there's only one configuration manager that handles all settings consistently. No matter which part of the application accesses the configuration, it will always reference the same up-to-date settings, preventing any discrepancies and ensuring smooth, reliable operation across all environments. Why singleton? Using the singleton pattern for a configuration manager ensures that the entire application works with a single, consistent set of configurations. This prevents different parts of the system from accessing outdated or conflicting settings, which can lead to bugs or misbehavior. With a singleton, any updates made to the configuration are immediately reflected across the entire application, so you don't have to worry about synchronizing settings manually. Moreover, a singleton configuration manager avoids the performance hit of constantly reading configuration files or settings from storage, as the settings are loaded once and then used throughout the application. This leads to more efficient and reliable management of configurations. Expanded use case. In an e-commerce platform, managing configuration settings like discount pricing or holiday promotions is critical for a seamless customer experience. If multiple instances of the configuration manager were allowed, different parts of the platform could end up using outdated promotion settings, leading to inconsistency. Some customers might see the promotion while others don't, or the wrong prices might be applied. Using a singleton configuration manager ensures that all services across the platform are accessing the same up-to-date configuration. This keeps the system synchronized, reduces errors, and provides a consistent shopping experience for all customers. Practical implementation. In this example, we implement a singleton pattern to manage configuration settings for an application. As explained earlier, the singleton pattern ensures that only one instance of the class is created throughout the entire application. This is particularly useful in scenarios like configuration management, where you need a single, centralized source of truth that can be accessed and modified from different parts of the application while maintaining consistency. The singleton pattern prevents the creation of multiple instances, ensuring that all parts of the application refer to the same configuration object. The singleton config manager class achieves this by overriding the underscore underscore new underscore underscore method, which controls how new instances are created. If no instance exists, the method creates a new one and initializes the configuration using the underscore initialize underscore config method. If an instance already exists, it simply returns the existing one, ensuring that only one instance is ever created. The configuration settings are stored in a dictionary, simulating loading from an external source like a file or environment variables. The class provides methods such as get underscore config and update underscore config to retrieve and modify configuration values. Since both config1 and config2 refer to the same singleton instance, any updates made to the configuration through config1 are immediately reflected when accessed via config2. For instance, when config1.update underscore config debug underscore mode false is called, this change is also reflected in config2.get underscore config debug underscore mode because both variables point to the same configuration object. This use of the singleton pattern for configuration management ensures that all parts of the application work with a consistent set of configuration values, regardless of where the configuration is accessed or updated. It eliminates the risk of having multiple conflicting configuration objects, making it easier to maintain and update settings across the entire application. 4. Caching system. In a caching system, applying the singleton pattern ensures that all parts of the application access and update the same cache, improving both efficiency and consistency. Without a singleton cache, different parts of the application might create separate caches, leading to redundant storage and inconsistent data. For example, if one part of the app updates a cached value and another part uses a different cache, the data might be out of sync, causing errors or outdated information to be served. A singleton cache avoids these issues by maintaining a single unified cache that all components can use, improving overall performance and reducing memory overhead. Why singleton? Using a singleton cache ensures that the application efficiently accesses and manages data in one place, preventing duplication and saving me memory. Without it, different parts of the system might create separate caches, leading to inconsistent or redundant data storage. By centralizing the cache, the singleton pattern ensures that data consistency is maintained across the application, and cache expiration or invalidation policies can be uniformly applied. This leads to better memory management and more predictable behavior when retrieving frequently accessed data. Expanded use case. Yo, in this expanded use case, a singleton caching system can dramatically improve the performance of an online store by ensuring that product data, such as prices and availability, is stored in memory and shared across the entire application. Instead of querying the database each time a user views a product, the application can quickly read the cached data, reducing load on the database and speeding up the user experience. This ensures faster response times and prevents unnecessary database queries, improving overall efficiency and scalability, especially during high traffic periods. Practical implementation. In this example, we implement a singleton pattern to create a caching system where only one instance of the cache exists across the entire application. As explained in the earlier response, the singleton design pattern ensures that no matter how many times you attempt to create an instance of the class, only one instance is created and used. This pattern is particularly useful when you need a centralized resource like a cache that is shared across multiple parts of an application to avoid duplication and maintain consistency. The key to achieving this is the underscore underscore new method, which checks if an instance of the class already exists. If underscore instance is none, meaning no instance has been created, it creates a new instance and initializes the cache by calling underscore initialize underscore cache. If an instance already exists, it simply returns the existing instance, ensuring that all references point to the same cache. The cache is stored as a dictionary where key value pairs can be added, retrieved, or invalidated removed. By implementing methods like set underscore cache, get underscore cache, and invalidate underscore cache, we can add, access, and remove entries from the shared cache. The singleton behavior ensures that both cache1 and cache2 reference the same instance. When you cache a value using cache1, you can retrieve it using cache2 because they both operate on the same underlying cache. This is confirmed when print cache1 is cache2 returns true, showing that both variables refer to the same object in memory. This implementation demonstrates how the singleton pattern can be applied to a caching system, providing a consistent and shared cache across the entire application. This design prevents issues like multiple caches being created in different parts of the program, which could lead to inconsistencies. Instead, the singleton pattern ensures that all cache operations, whether adding, retrieving, or invalidating entries, are performed on the same shared instance, making the cache reliable and efficient. 6. Conclusion. In this video, we've explored the singleton pattern in depth, understanding its fundamental principles and how it ensures that only one instance of a class is created and accessed throughout the application. We discussed the key benefits of singleton, such as its role in efficient resource management and consistent behavior across the system. We also touched on potential pitfalls such as ensuring thread safety and avoiding instance duplication. Lastly, we applied the pattern to a real-world use case with a database connection example, highlighting how it can optimize resource usage and prevent common issues in large-scale applications. And that's it for the singleton design pattern in Python. As you've seen, it's a straightforward but incredibly useful pattern, ensuring that you only ever have one instance of a class. This pattern is perfect when managing shared resources like database connections, configuration settings, or logging instances. I hope this video helped clarify how the singleton pattern works in Python. If you found this helpful, don't forget to like, share, and subscribe for more coding tutorials and interview prep tips. Thanks for watching and see you in the next video.